Hey everyone! Today we're exploring logarithms, a crucial topic in general mathematics for SSS1 students. Don't worry if it sounds complicated, we'll break it down step by step like friendly teachers do. Let's start with what you already know: indices or exponents. When we write 2 to the power of 3 equals 8, we have a base of 2, an exponent of 3, and a result of 8. This means 2 multiplied by itself 3 times gives us 8. Now what if we want to undo this operation? What if someone asks 2 raised to what power equals 8? This is where logarithms come in. They help us find that missing exponent. Logarithms are the undoing of exponents. They ask the question, what power gives us this result? The image shows us this relationship clearly. If 2 to the power of 5 equals 32, then the logarithm base 2 of 32 equals 5. The logarithm gives us back the original exponent. Here's the beautiful inverse relationship. Exponents take us from base and power to result, while logarithms take us from base and result back to the power. They're perfect opposites, like addition and subtraction or multiplication and division. This comparison shows how exponent laws and logarithm laws mirror each other perfectly. Just as exponents have rules for multiplication, division, and powers, logarithms have corresponding rules. This isn't a coincidence, it's because they're inverse operations. Understanding one helps you understand the other. Here's your key takeaway. Logarithms are simply the inverse of exponents. They help us find unknown exponents in equations. If you understand indices, you're already halfway to mastering logarithms. The laws mirror each other perfectly, making them easier to remember and apply. You've got this. Now that you understand the fundamental relationship between logarithms and indices, you're ready to build on this foundation and explore more advanced concepts. What exactly is a logarithm? This is the fundamental question we need to answer. A logarithm is simply the inverse operation of exponentiation. Let me show you this relationship mathematically. If we have an exponential equation where b raised to the power x equals y, then the logarithm form tells us that x equals log base b of y. Let's break this down with a concrete example. If 2 raised to the 5th power equals 32, then we can say that log base 2 of 32 equals 5. The logarithm, which is 5, tells us the exponent we need. Here's another way to think about it. Let's try a different example. What power do we raise 3 to get 81? We can write this as 3 to the what power equals 81. Now let's look at a special property of logarithms. When we have a base raised to the power of a logarithm with the same base, something interesting happens. The result equals the input of the logarithm. Let's summarize the key takeaways. Logarithms are the inverse of exponents. They tell us what power we need to raise a base to get a specific number. The relationship between exponential and logarithmic forms is fundamental to understanding how logarithms work. Base 10 logarithms are everywhere in mathematics and science. They're so common that we call them common logarithms for a reason. A common logarithm uses 10 as its base. We can write it as log base 10 of x, or simply log of x when the base 10 is understood. The fundamental relationship is this. If y equals 10 to the power of x, then x equals log base 10 of y. This means we're asking the question, to what power must we raise 10 to get y? Let's work through some examples to make this crystal clear. First, let's find log base 10 of 100. Let's try another example. What about log base 10 of 1000? Here's a tricky one. What about log base 10 of 10 itself? And here's an interesting case. What about log base 10 of 1? Let's visualize how exponential functions and logarithms are related. This graph shows how 2 to the power of x grows exponentially. Now let's summarize the key patterns we've discovered with common logarithms. These patterns will help you solve logarithm problems quickly. Remember, common logarithms are just asking one simple question. To what power must we raise 10 to get our number? Once you understand this fundamental concept, working with base 10 logarithms becomes much easier. Every logarithm consists of 2 distinct parts that work together to represent the complete logarithmic value. Understanding these components is essential for working with logarithm tables and calculations. The characteristic is the integer part of the logarithm, while the mantissa is the decimal part. For example, in log base 10 of 2.56 equals 0.408, the characteristic is 0 and the mantissa is 0.408. For numbers greater than or equal to 1, the characteristic equals the number of digits before the decimal point minus 1. For example, 256 has 3 digits, so the characteristic is 2. Similarly, 25.6 has 2 digits before the decimal, giving a characteristic of 1. For numbers less than 1, the characteristic becomes negative. The table shows how the characteristic is calculated based on the number of zeros after the decimal point. For 0.5, there are no zeros after the decimal, so the characteristic is negative 1. For 0.024, there is 1 zero, making the characteristic negative 2. The rule is simple. For decimal numbers, the characteristic equals negative 1 minus the number of zeros immediately after the decimal point. This pattern helps us quickly determine the characteristic without complex calculations. The mantissa is always found using logarithm tables and has several important properties. It's always positive between 0 and 1 and remains the same for numbers with the same significant digits. For example, 2.56, 25.6, and 256 all have the same mantissa of 0.408, but different characteristics. Remember these key points. Every logarithm equals its characteristic plus mantissa. The characteristic is the integer part that depends on decimal position, while the mantissa is the decimal part found in tables. Understanding these components is crucial for working with logarithms effectively. Logarithms have 3 fundamental rules that make complex calculations much simpler. These are the product rule, quotient rule, and power rule. Understanding these rules will transform how you work with logarithms. The product rule is our first logarithm rule. It states that the logarithm of a product equals the sum of the logarithms. This means we can break down complex multiplications into simple additions. Here's a practical example. Instead of finding log base 10 of 100, we can break it down as log of 10 times 10, which becomes log of 10 plus log of 10. Since log base 10 of 10 equals 1, we get 1 plus 1 equals 2. The quotient rule handles division in logarithms. It states that the logarithm of a quotient equals the difference of the logarithms. This transforms division into subtraction, making calculations much easier. For example, log base 10 of 1000 divided by 10 becomes log of 1000 minus log of 10. Since log of 1000 is 3 and log of 10 is 1, we get 3 minus 1 equals 2. This confirms that 10 squared equals 100. The power rule is incredibly useful for handling exponents. It states that the logarithm of a number raised to a power equals the power multiplied by the logarithm of the number. This converts exponents into simple multiplication. Here's how it works in practice. Log base 10 of 10 to the power of 3 becomes 3 times log base 10 of 10. Since log of 10 equals 1, we get 3 times 1 equals 3. This confirms that 10 cubed equals 1000. These 3 rules work together to simplify complex logarithmic calculations. They transform multiplication into addition, division into subtraction, and exponents into multiplication. This makes logarithms a powerful tool for solving mathematical problems. Remember these key takeaways. The product rule turns multiplication into addition. The quotient rule turns division into subtraction. The power rule turns exponents into multiplication. These rules are the foundation for working efficiently with logarithms in mathematics. Logarithm tables are powerful tools that help us find logarithms and anti-logarithms without complex calculations. Before calculators, these tables were essential for mathematical computations. To find the logarithm of a number using tables, we follow 3 main steps. First, express the number in standard form. Second, use the table to find the mantissa. Third, determine the characteristic based on the power of 10. Let's work through a practical example. Suppose we want to find the logarithm of 152.7. First, we express this in standard form as 1.527 times 10 to the power of 2. Now we use the logarithm table to find the mantissa. We look up 1.527 in the table. The table shows us the decimal part of the logarithm, which is the mantissa. The characteristic comes from the power of 10 in our standard form. Since we have 10 to the power of 2, our characteristic is 2. The complete logarithm is the characteristic plus the mantissa. Now let's learn about anti-logarithms. An anti-logarithm is the reverse process. We start with a logarithm value and find the original number. If log of x equals 2.176, then the antilog of 2.176 equals x. To find anti-logarithms, we use anti-logarithm tables. These tables work in reverse. We look up the mantissa to find the corresponding number, then adjust using the characteristic to get our final answer. Here are the key takeaways for using logarithm tables effectively. Always express numbers in standard form first. Remember that the characteristic comes from the power of 10. Use interpolation for values between table entries. And practice regularly to build confidence with table lookup. Logarithms aren't just abstract mathematical concepts that exist only in textbooks. They're powerful tools that help us understand and measure phenomena in our everyday world. One of the most important uses of logarithms is measuring earthquake magnitudes using the Richter scale. This scale helps us compare earthquakes that can vary tremendously in strength. The Richter scale uses logarithms because earthquake energies can differ by millions of times. A magnitude 7 earthquake releases about 1,000 times more energy than a magnitude 5 earthquake. Another common application is measuring sound intensity using the decibel scale. This logarithmic scale helps us compare sounds from the faintest whisper to the loudest jet engine. The decibel formula uses logarithms to compress the huge range of sound intensities we can hear. A sound that's 10 decibels higher is actually 10 times more intense. The pH scale is another logarithmic scale that measures how acidic or basic a solution is. This scale is crucial in chemistry, biology, and environmental science. The pH scale uses negative logarithms to measure hydrogen ion concentration. A solution with pH 3 is 10 times more acidic than one with pH 4 and 100 times more acidic than pH 5. Logarithms also have important applications in finance, data analysis, and many other fields. They help us work with exponential growth, compound interest, and large data sets. The key takeaway is that logarithms help us make sense of phenomena that span enormous ranges of values. They transform multiplication into addition and make complex calculations much simpler. Working with logarithms can be tricky, and students often make similar mistakes. Understanding these common errors will help you avoid them and solve logarithm problems with confidence. The first major error is forgetting the order of operations, known as BODMAS. This stands for brackets, order, division, multiplication, addition, and subtraction. Let's see how this applies to logarithm calculations. Here's a common mistake. When calculating log of 2 times 5 plus 3, students often work left to right instead of following BODMAS. The wrong way gives log of 13, but the correct way, following order of operations, gives log of 23. The second common error involves simplifying fractions incorrectly. Many students make mistakes when reducing fractions in logarithm expressions. Let's look at the proper methods. A common mistake is canceling terms incorrectly. For example, when simplifying log of 12 over 4, students might try to cancel the 2's, but this is wrong. The correct approach is to simplify 12 divided by 4 equals 3 first, then take log of 3. The third error is not reading questions carefully. Students often miss important details like the base of the logarithm or specific instructions about the format of the answer. Notice this question asks for log base 2 of 16, not log base 10. Also, it specifically asks for an integer answer. Students who don't read carefully might use the wrong base or give a decimal answer. The fourth major error involves handling negative characteristics incorrectly. When working with logarithms of numbers less than 1, the characteristic becomes negative, and this confuses many students. The key is to remember that when the number is less than 1, the characteristic will be negative. Don't forget the negative sign, and be careful with your arithmetic when combining the characteristic and mantissa. Here are the key takeaways to help you avoid these common logarithm errors. Always follow BODMAS, simplify fractions step by step, read questions twice, and pay special attention to negative characteristics. Remember, practice makes perfect. The more you work with logarithms while keeping these common errors in mind, the more confident you'll become. Take your time, double-check your work, and you'll master logarithms successfully.